Hello friends, this video on dual nature of radiation and matter part 5 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 4 before going ahead with part 5. So what is photoelectric effect? The phenomenon of emission of electrons from a metal by incident electromagnetic radiation, right? So that is what we saw till now. Photoelectric emission was also the same thing, emission of electrons by incident electromagnetic radiation. So the electrons which are emitted in this case are known as photoelectrons, and the current constituted due to the flow of these photoelectrons is known as the photocurrent. This is how things happen. If this is your metal surface, the metal surface will obviously have free electrons because every metal has free electron. They are good conductors, right? So when this electromagnetic waves fall on this metal, the electrons get ejected, and this is photoelectric effect. Substances emitting electrons when illuminated by visible light are known as photosensitive. So those kind of substances are known as photosensitive. That means if you give a light of any suitable frequency, somewhere around the range of visible light, they emit electrons. So they are known as photosensitive materials. Almost all metals, they have free electrons. All metals have free electrons, and they are all sensitive to some or the other light. Depending upon the electronic configuration of the metals, they will react to the light. For example, they will react to their corresponding frequencies. For example, if we take the example of sodium. Sodium has only one valence electron. Therefore, that one valence electron can be easily taken out from the sodium. So sodium needs a light of not very high frequency or something like that. So sodium is photosensitive to visible light. Whereas if we take the example of magnesium, it has got two free electrons. So it needs little more energy to take out those two free electrons out of it. So magnesium is sensitive to ultraviolet light, which has a little more frequency than that of the visible light. So that is how, all metals are they can show photoelectric effect, but it will react to what kind of frequency range, that depends upon the electronic configuration of the metal, because the electronic configuration of the metal tells us about the work function of the metal, and that decides the threshold frequency at which the photoelectric effect will start taking place. Let us now look at the detailed experimental study of photoelectric effect. As I mentioned before, that Halbach and Lenard, they wanted to know how the photocurrent will vary with the intensity, with the frequency of the incident light. So what are the factors that actually determine the photocurrent? So this experimental setup was used to study this. It looked somewhat like this, which had an evacuated tube. As you can see here, this is the evacuated tube. Inside this, they had an emitter. This is your emitter. The C denotes cathode and the A denotes anode. So the emitter is a photosensitive plate. When I talk about a photosensitive plate, that means it is a little more sensitive to visible light. It can easily emit electrons when it is illuminated by light. There is another metal plate which acts as collector. So we choose this emitter in such a way that it is little more photosensitive as compared to the other metal plate, right? So now we use a monochromatic light of short wavelength. Okay. Then we have a battery which maintains to create an electric field inside the tube, and to maintain a potential difference between the two plates. We have a voltmeter to measure the potential difference between the two plates. And we also have an ammeter which will measure the amount of current flowing through the circuit. That is, which will measure the photocurrent actually. So in this case, what happens when this monochromatic light falls on this emitter, electrons will get emitted, right? So what happens when the light falls on this photosensitive plate? Electrons get emitted from this. They get attracted towards the other metal plate, that is the collector, And due to the flow of this electron from the photosensitive plate towards the metal plate, electric current gets constituted. And this electric current is nothing but the photocurrent, and the photocurrent is measured by the ammeter. So it was a very simple experiment which was carried out. But this experiment was helpful in studying the variation of photocurrent as we change the frequency of the incident light, as we change the intensity of the incident light, as we change the potential difference between the two plates. So we will see the conclusion of this experiment one by one. So the first conclusion which we will talk about is the variation of photocurrent with the intensity of radiation. What happened when we tried changing the intensity of the incident light? How did the ammeter respond? I mean, what was the magnitude of the current flowing through the circuit? It was done like this. The frequency of the incident light was kept fixed. The potential difference between the two electrodes was kept fixed. So the only thing that was varied in this case was the intensity of the radiation. So when we increase or decrease the intensity of the radiation, it was observed that the photocurrent increased linearly with the increase in intensity. As we increase the intensity, the photocurrent also increases with time. Now, what is this photocurrent actually? Photocurrent is nothing but the number of photoelectrons per unit time, right? What is current? Current is nothing but number of electrons flowing per second. Similarly, it is number of photoelectrons per second, right? So that is photocurrent. So it was seen that as the intensity of the incident light was increased, the number of photoelectrons emitted also increased with time. So if the number of photoelectrons emitted keep increasing, the photocurrent will also increase, right? So photocurrent varies linearly with the intensity of light. So we want more photocurrent, we have to provide light of more intensity. The next one was variation of photocurrent with potential. That means what happened if we change the potential difference between the two plates? Will the photocurrent remain the same or it will change? And if it will change, how will it change? So, well, when we talk about this potential, we will talk about two types of potential. One is a positive potential and the other one is a negative potential. One is positive potential and the other one is negative potential. What is positive potential? Positive potential is the scenario when the collector, this is my collector and this is my emitter. So this is my photosensitive plate where light is falling, and this is the collector where the electrons are coming. Now if this is positive with respect to emitter, that is positive potential. When we say that we are talking about positive potential, how photocurrent is varying with positive potential, that means we are keeping the collector at a higher potential as compared to the emitter. When we talk about negative potential, I mean that the collector is at a negative potential with respect to the emitter. So we are keeping the collector at a lower potential as compared to the emitter. So this, I just explained you the terminologies, because now when we discuss about the variation of photocurrent, we will use these two terminologies, right? Now, this was how it looked like. If we plot a graph, this is my origin. Now, as the positive potential keeps increasing, I mean, first you consider the first scenario. First you consider the scenario of positive potential. Positive potential, that means the collector is at a positive, this collector is at positive with respect to the emitter. So the metal plate is positive with respect to the photosensitive plate. So since it is highly positive, so whatever electrons are coming out from this emitter, they will get attracted towards it. So the electrons will keep flowing towards the collector. That means as the positive potential is increased, more and more electrons will keep flowing towards collector. So the photocurrent will increase. So as you can see, initially the photocurrent is increasing. But gradually, if you see, the current saturates. So this is a saturation level. That means beyond this, the current is not increasing. Even though the potential keeps increasing, but the current remains the same. Why does this happen? This happens because this is also a metal, right? So this metal also has some fixed number of electrons. So a time comes when all the free electrons of the photosensitive plate has already moved towards the collector, right? In that case, even if you keep increasing the positive potential, there is no point, right? There are no more photoelectrons to move to flow. Therefore, the current saturates. It cannot increase beyond that. Whatever photoelectrons were there, that is moving. Beyond that, it is not moving. Now, why is it happening like that? We will talk about all these things when we will try to explain this photoelectric effect. Right now, we are only talking about the experiment which was performed to see the variation of photocurrent by changing different parameters. So we will just look at the results of the experiment here. So the result was that as we keep increasing the positive potential, photocurrent increases with increase in positive potential till the current reaches a saturation value. So this was the first observation. Now what was done in the second part of the experiment? What was done? The collector was kept at a negative potential with respect to the emitter, right? So now the collector is at a lower potential, and now this negative potential is also sometimes known as retarding potential. Now when this negative potential is increased, that means the potential value is increasing but on the negative side. Now when this was increased, it was found that the current kept decreasing. This is because now this is negative. Now if this is negative, the electrons which is coming out from the emitter, they will get repelled by the collector. So many of the electrons will get repelled and they will go back to the emitter, but there will be some electrons who will still be able to reach the collector. Who will be those electrons? The one who has more energy. That means earlier all the electrons which were emitted by the emitter was getting moved towards the collector, right? Now what will happen? Many of the electrons will get repelled by the collector because the collector is at a lower potential. But some of the electrons which have maximum energy, which have maximum velocity, they will still be able to reach the collector. So that means the current will not drop to zero, but the current will decrease, because earlier the contribution towards current was by all the photoelectrons, but now the contribution has decreased because some of the electrons are getting repelled by the collector. So they are not moving towards the collector. So now lesser number of photoelectrons are moving towards the collector, therefore the photocurrent is lesser. And it was found that at a particular value of potential, the photocurrent became zero. So this particular value of the potential or the retarding potential is known as the stopping potential. So the stopping potential is nothing but the potential at which the photocurrent drops to zero. That means beyond this potential, there is no flow of current at all. That means what happens at this stopping potential? At this stopping potential, even the most energetic electron, that means the electron which had the maximum kinetic energy, even that electron is failed to reach the collector. So when none of the electrons, because earlier the situation was, let us suppose initially when this collector was at a positive potential, at that time if 100 electrons were reaching the collector, when I kept the collector at a negative potential, not 100, some 70 were able to reach. Let us suppose 30 were getting repelled. Now as I keep increasing the negative potential, the number of electrons reaching the collector will gradually decrease from 70 to 60 to 50 to 40. At last it will become 1. That last electron which is able to reach the collector, that is the electron which had the maximum kinetic energy. But if you still keep increasing the negative potential, that an electron with the maximum kinetic energy will also not be able to reach the collector. So there we get the stopping potential. That means there is no electron which is actually reaching the collector, and as a result there is no current flow. Therefore the photocurrent is zero. Right? So when we talk about this stopping potential, what happens when the photocurrent drops to zero? Actually, the maximum kinetic energy of the photoelectron becomes equal to E into V0, where V0 is the stopping potential. So the charge on the electron multiplied by the potential applied becomes equal to the maximum kinetic energy of the most energetic photoelectron. So now even the most energetic electron cannot reach the collector, because as long as there was some current flowing, this kinetic energy, the maximum kinetic energy, was greater than this. Right? So I hope you understood how we arrived at this expression and what is the concept of stopping potential. Okay. So the second part was photocurrent decreases with increase in retarding potential till it becomes zero. So these were the two important observations from this photoelectric effect experiment. So now let us quickly talk about stopping potential. We will just review it. I already explained you the concept. Stopping potential is the minimum negative potential or retarding potential given to a plate for which the photocurrent becomes zero. It is also known as cutoff potential because at this point the photocurrent is getting cut off. That is why it is called cutoff potential. For a given frequency of incident radiation, stopping potential is independent of the intensity. Let us suppose if the frequency is kept constant, and if you keep changing the intensity of incident light, the stopping potential will remain the same. So that means stopping potential depends on frequency of the incident radiation and it does not depend upon intensity. So stopping potential depends on frequency and it does not depend upon intensity. We will look at it also graphically. So what are the factors on which it depends? It depends on frequency of the incident radiation. It also depends on the material of the emitter plate. See, material of the emitter plate will always play a very important role because it is the material of the plate which decides how much is the work function, how much energy is actually required to be given to emit an electron. Therefore, the threshold frequency also depends on the material of the plate. The work function also depends upon the material of the plate, and now the stopping potential also depends upon the material of the plate, because end of the day everything depends upon the electronic configuration of the metal which is being used. How eager or how difficult it is for the metal to lose its valence electron. So everything depends upon that. Right? So I hope I am able to explain you what is the concept of stopping potential. Now let us quickly look at what we spoke just now. How is it that stopping potential does not depend upon intensity and it depends upon frequency? So a plot, before I told you how photocurrent varies with potential. In this case, you see, this is my positive potential, this side my negative potential is increasing. So if you see, for different intensities of light, we used 3 different intensities of light, I1, I2 and I3, and we saw when we plotted their graph, we actually performed these experiments, right? And we measured the values of photocurrent by increasing the positive potential, again by increasing the negative potential. So when we plotted them on a graph, we saw that the value of stopping potential for all the 3 intensities was the same. So this shows that stopping potential does not depend upon the intensity of light, right? So this graph shows that stopping potential does not depend on intensity of the incident light, right? But what depends upon the intensity of incident light? The saturation current. If you look at it, for I1, this is the saturation current. For I2, this is the saturation current, and for I3, this is the saturation current. So from here we see that the saturation current increases with increase in intensity. That's because we told before also, right? When the intensity of the incident ray increases, our conclusion 1 was that the photocurrent increases with increase in intensity. So in all the 3 sets, we have increased the intensity. Therefore, the photocurrent has increased, and photocurrent is nothing but the saturation current is nothing but this photocurrent, right? The maximum value of this photocurrent. Therefore, each time we increase the intensity, the value of maximum photocurrent also increases. So, saturation current depends upon the intensity of incident light, but stopping potential does not depend upon the intensity of incident light. So far we discussed about 2 things. dependence of photocurrent on intensity, and dependence of photocurrent on potential. Now the third conclusion was the variation of photocurrent with frequency of incident radiation. We will now see if the photocurrent changes when we change the frequency of the incident radiation. Now for this also, experiments were performed for 3 different values of intensity, like for 3 different values of frequency. Like how we performed it for intensity, similar experiment were performed by taking different values of frequency. So first we took then incident light of frequency nu1, then nu2, then nu3, and then similarly we first increased the positive potential and measured the values of photoelectric current, then we increased the negative potential and measured the values of photoelectric current at each point, and then we plotted the graph. And what did we see? We see that the saturation current is the same for all different frequencies. That means saturation current does not depend upon frequency. But the values of stopping potential changes with frequency. As the frequency, in this case if you see, nu3 is greater than nu2 is greater than nu1. That means for maximum frequency, this is the maximum frequency. For maximum frequency, the stopping potential is greater. And for minimum frequency, the stopping potential is lesser. That means stopping potential, that is V0, is directly proportional to the frequency of incident light. Right? So we saw 2 things. Saturation current depends upon intensity and stopping potential depends upon frequency. So this was one observation from this. Now what about photocurrent? What is the variation of photocurrent with frequency? The photocurrent, if you look here, photocurrent does not depend on frequency much. Because the saturation current also, if you see, it is not, it is the same for all different frequencies. So frequency doesn't play an important role in changing or in increasing the photocurrent, but it changes the stopping potential. So frequency, as you keep changing the frequency, if you want more current, you have to change the intensity. But if you want to change the stopping potential, that means if you want to change the duration for which the amount of photocurrent should flow, in that case you have to change the frequency, because stopping potential decides for how long photocurrent will be there, for how long electric current will flow, right? So when we plot the graph of this stopping potential with frequency, we see that it increases with increase in frequency, but initially it is 0 for some time. That means this value of frequency is the threshold frequency below which no photoelectric emission took place. So the experiments told that there was a minimum value of frequency above which the photoelectric emission took place. Below that value of frequency, photoelectric emission did not happen at all. And when we talk about the amount of photocurrent can be governed only by intensity. It is not dependent on frequency. If you think that by increasing the frequency, you can increase the photocurrent, that is not possible, because increasing the frequency will affect the stopping potential. It can make the amount of current whichever is flowing to flow for a longer time. It will drop to 0 after some time, because it will increase the value of the stopping potential. So the time when the photocurrent drops to 0, that will come little later, because that will need little more potential, right? So this is how we studied the variation of photocurrent with frequency. So this introduced again a new term, that is threshold frequency. It is the minimum frequency of incident radiation below which photoelectric emission does not occur. So it is also known as cutoff frequency. So the way we spoke about cutoff potential, where the photoelectric emission does not occur. So that was the potential corresponding to which there was no photoelectric emission. This is the frequency corresponding to which there is no photoelectric emission. And you saw that both are related, right? Because that potential, the cutoff potential, is actually determined by the frequency. It varies with metals. I don't think I need to explain this point again because every metal will have different electronic configuration. So let us have a quick conclusion of the experiment which was performed on photoelectric effect. So taking into conclusion 1, 2 and 3 together, what all did we see? We saw that photocurrent is directly proportional to the intensity of incident light. If we increase intensity, current will increase. Saturation current is proportional to the intensity of incident light. So all currents are proportional to the intensity, right? Stopping potential is independent of intensity. Stopping potential has nothing to do with intensity. There exists a threshold frequency for every material below which no photoelectric effect takes place. Stopping potential and maximum kinetic energy of photoelectrons increases linearly with frequency. So this I have told you very clearly, how stopping potential increases with frequency. However, what about this maximum kinetic energy? I mentioned before, right? What is stopping potential? That means a potential where the photocurrent will drop to zero. That means at stopping potential, the electron which has the maximum kinetic energy, that electron will also not be able to reach the collector electrode, right? That means at stopping potential, the energy due to the work done by the stopping potential becomes equal to the maximum kinetic energy of the photoelectron, right? That's what I had mentioned before. That is K max becomes equal to E V naught. So now if V naught, that is stopping potential, if it increases linearly with frequency, so this maximum kinetic energy will also increase with frequency. What is this maximum kinetic energy? It is basically the maximum kinetic energy that a photoelectron can have. Like when light falls on the emitter, photoelectrons are emitted. So what is the maximum kinetic energy that the photoelectron can have? It is that maximum kinetic energy. Photoelectric effect is an instantaneous process. The experiment also showed that as soon as light fell on the emitter plate, electrons got emitted. So there was no time lag in between. As soon as light fell, immediately electrons got emitted. So it was an instantaneous process. So this was photoelectric effect experimentally. I mean, experimentally, all these were the observations. Now, whatever we see experimentally, they are always true. Correct? Because that is something which is happening. It is not an hypothesis. It is not an imagination. It is something which is happening in reality. That means whatever is written on this screen right now, they were all experimentally observed and proved. Experimentally, it was calculated and proved that, okay, saturation current is not depending on intensity. For different intensities, they tried it. Similarly, for different frequencies, they did the entire experiment and then they found that stopping potential is dependent on frequency. So all these things are true, right? So now the question is, photoelectric effect is a phenomenon of light. Light is falling on something and it is causing electron emission. Now, till now, the scientists have told that light is of wave nature. So if light is of wave nature, then wave nature of light should be able to explain why this photoelectric effect. So the wave nature of light should be able to explain properly all these 6 points which are listed on this screen. So thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.